Hello, I made a robot. This is the Yambot4. I was looking for an out-of-the-box, low-cost robot to practice ROS programming with. I didn't find one online, so I made one. So the goals of this project were to make something affordable and easy to build. In the future, I want to build multiple of these and have them run as a swarm. With the modular sensor attachment in the front and rear, I want to be able to have different types of Yambots run different jobs in the swarm. I designed the chassis and wheels in Fusion 360. I printed them on my Bamboo Labs A1 Mini. The wheels are printed in TPU. I also printed sensor modules on the front and rear. They can be swapped in and out with other modules. Right now, there's a time-of-flight 2D LiDAR sensor on the front and an IMU sensor on the back. I designed 3 custom PCBs for this project in Fusion 360, one for the main board that runs the ESP32S3 processor, and then 2 for each sensor module board. It is programmed with a USB-C connector. It runs on 2 LiPo batteries. It turns 2 brushless DC motors with 2 encoders each. It has an H-bridge to control these motors. It uses an I2C communication bus to communicate to the 2 sensor modules. The first one is the ST time-of-flight 2D LiDAR distance sensor in the front. This captures range information from the front of the system. The second is an ST IMU in the back, and this captures IMU data. There's a status LED on the PCB to communicate the status of the system, and there's also an antenna to communicate the ROS data over Wi-Fi to the computer. The software runs on FreeRTOS. There's around 10 threads that will run asynchronously on the S3's 2 cores. It runs microROS, which is a version of ROS for microcontrollers. This interfaces to a ROS2 terminal running on a PC over Wi-Fi connection. I'm using the Jazzy release of ROS2 at the time of this video. There's a dedicated thread for each publisher and subscriber on the Yambot. The motor control system consists mainly of 2 things: turning the motors from the subscribed command velocity over ROS, and second, reading the encoder information and then publishing this as a twist message over ROS. The range system provides the range of the closest object in front of the robot. The sensor board collects range data from the time-of-flight 2D LiDAR sensor. It sends this data via I2C communication to the ESP32. Then the range thread in the ESP32 handles this data and then publishes the range data as a range message in ROS. The IMU system behaves very similar to the range system. The sensor module in the rear of the system collects IMU data. It sends this data via I2C to the ESP32 processor. Then the IMU thread will handle this data and publish this data as an IMU message over ROS. Everything in this project was planned with Atlassian tools. I tracked progress for everything in Jira. I put together system documentation in Confluence and Draw.io. The code is managed in Bitbucket and documented with Doxygen. It runs a pipeline in Jira to build everything and compile the Doxygen documentation as well. Thanks for watching.